So the topic for today's lecture is the derived category. And this will be our main application of the techniques of triangulated categories that we developed in the previous several lectures. So let me start with the quite simple definitions. These definitions you've probably seen already many times. So let's fix an additive category. So let A be an additive category. So then I can define the category of complexes. Complexes of the category A. So what are objects? Well, of course, objects are just sequences of the objects in the, say this is x p minus 1, then we have next object xp, and then I have next object xp plus 1, etc. So in principle, this could be infinite sequence on the left and on the right. So of course, if I want to define a category, I need to define objects and morphisms. So these are my objects. So this, if I want to define objects of the category of complexes, these are the objects. But I have all these maps. So this map is dp minus 1, dp, etc. And of course, I want the property that if I apply two maps, so I take the composition of two consecutive maps, I'm supposed to get 0. So that's a complex. Now let's define maps, so the homes between two complexes. So, and for shortness, I'm going to write this something like x with a bullet. So this is notation for the complex. So suppose I have now complex x and another complex y. I want to define what I think about the homes in this category. Again, the definition is quite straightforward. You just write the first complex, write the second complex, and then the map between two such complexes is just, well, a family of maps between the objects. So here I have a map fp minus 1, fp, fp plus 1, such that all the squares in this diagram, so infinitely many squares in general, are all commutative squares. So I hope there is nothing surprising in this definition. Now I have a quite trivial remark. So if the category started with A is additive, as I assume, then of course this category of complexes is again additive. You can think about this for a couple of minutes and you see this is completely clear. And the second remark, so 1, 2, if I additionally assume that A is not just additive, if this is abelian, so A is abelian, then the category of complexes is again abelian. So you need to check that there are kernels and co-kernels, but clearly you can define this kind of component-wise for all the maps and prove that the category is abelian. So very easy remarks if you think about them. Now I want to define the homotopic category, and I'm going to do this kind of in two steps. First, I'm going to define the graded, or sometimes it is called internal home between two complexes. So if you look at the definition here, all this, the map that I have, so I can call this map, say, f with a bullet. This is a map of degree 0. meaning that if I start with something that sits in xp, the map is mapping this to the yp. But in principle, I can consider maps that mapping xp, say, to the y to the p plus 1. That would be a map of degree 1. Right, so if I find home like this, the graded, so this is home with a bullet. Another notation, which is exactly the same, sometimes people write something like home between two complexes to indicate that this is graded. Now, what is the graded home? Well, we just consider, say, now maps take, say, f of degree I, say, I. So let's say that the degree of the map is I. This means by definition, or I can say equivalently, that f is in the home with the index I. Right, so this is that's the meaning of this symbol. If I'm saying that the map has degree I and use this notation for the degree, then this means that f is here, and it means that if I consider the components, say I take this map f, and I want to understand what the component p is doing, so this would be a map from the, say, some x p to the y p plus I. So this thing is shifting the degree by I. Of course, I could be any integer. So remark, in the definition of the category of complexes, the degree of f is of course 0. Okay, so but this is this object only as a kind of graded abelian group, right? So this is with this degree, we can consider this as a graded abelian group, but also I can introduce the differential. Let me call this large D. So large D is the differential on the graded home. And this is defined by definition as follows. If I want to apply this D to some map F, say the map I consider has degree I, then I need to take the kind of the graded commutator of F with a D. And now we have a complete definition. When I'm writing something like a home with a bullet, this means that I have this graded abelian group with that differential. So, for example, if I want to take home in the category of complexes, so C of A, between two complexes x and y, I can say that this is the cycles, so Z0, of the home with the bullet. Right? Just by definition. So in the Z0, this will be everything in the kernel of this map, but the condition that F is in the kernel of this map is exactly the condition that the square is commutative. F commutes with the differential. Now, definition. The homotopic category of an additive category So I want to emphasize, to define homotopic category, it's enough to have additive category. It will be important later today. So the homotopic category of an additive category, H of A. So again, to define this category, I need to define objects. Well, the objects of the homotopic category are exactly the same as complexes. So this is the same as objects in the category of the complexes. But if I want to define Hom in the homotopic category, instead of taking just cycles, I take the quotients of the cycles by the boundaries. So I'm taking the zeros homology of the graded Hom. So sometimes informally people can write something like the homotopic category is H0 of the category of all complexes, but you need to understand that in this category of the complexes you don't just take maps of degree 0, but you take all the maps and you take that differential. So this is just notation. Let's say this is notation. A little bit informal. Okay. Well, if you haven't seen this definition of the homotopic category, you've probably seen the little bit different definition, right? What I need to take, well, in the homotopic category, Hom, if I want to understand the Hom in the homotopic category, well, I'm taking the Hom in the category of the complexes, right? And then I need to introduce an equivalence relation. Right, so I'm taking the quotient by B0. I can say that I have an equivalence relation. And what's the equivalent relation? If I have, say, F and G in the Hom C of A, X, and Y, well, when these two things are equivalent, so F is equivalent to G, if and only if, by definition, the difference F minus G, so this has to be, well, some large d of something, of H, right? By definition, well, I want to take the quotient by the boundaries, by the image of the differential d. But that's exactly the so-called homotopy between these two maps, right? Now, these two maps, F and G, has degree 0, so H has degree -1. And if I plug in this sign into the definition of the D, I'll get H D plus DH. So if you haven't seen definition in terms of the zeros cohomology of the graded Hom, you probably have seen definition like this. The definition of the homotopy between two maps of the complexes. That's the same thing. Of course, if you think carefully about that definition, you can find a little exercise hidden in the definition, right? You need to check that the composition respects the equivalence relation. But that's not so hard to do. Okay. So, remark, which is again easy. So the homotopic category is additive. But it's quite rarely can be proved that this homotopic category is abelian. So in fact, we're going to see this as a triangulated category. So that's the reason why we need this machinery of triangulated categories, because this category, which is interesting in many applications, in general is not abelian, but it has some additional structure, and the structure is being that this H of A is the triangulated category. Okay, but before we define the triangulated structure on this, I need kind of another definition and several easy exercises. Probably you know these exercises if you took something like algebraic topology, but still I need to formulate the statements. So first the definition, the mapping cone of a map of two complexes. So F is a map complex x to the complex y, and I want to define the mapping cone. So notation for this I'm going to use is C of F. So I need to define it as a complex. So first I define this as a graded abelian group. So in degree I have x of degree sitting in the degree I plus 1 plus yi, and the differential d. This is given by the following matrix, right? So now I have two components. So to write a differential, I need 2 by 2 matrix. So my convention is to use the following definition. So there could be different conventions, but let's fix these convention once until the end of this course. Okay, to formulate the next exercise, I also need some notation, well, notation or definition. So say another definition. I can define easily the shift function. So if I want to take a complex and shift this by 1, so in the degree I, there will be by definition x I plus 1. So this is how this works on the components of an object, and also need to define this on the differentials, and this is a shift of the differential with a minus sign. And if I want to define shift on the maps, I just shift the index. As you can see, this is clearly an autoequivalence. Right? So this T, which is the shift by 1, is a map from the complexes to the complexes. And this is invertible, and the inverse is just a shift by minus 1. Okay, so now I have exercise. So if you don't know this, I recommend you try to solve this. I'm not going to include this exercise in the next assignment because probably almost everybody saw this before in the algebraic topology. So now in this exercise I need an abelian category. So let A be an abelian category. So first, if F is the map of two complexes, then there is a short exact sequence of complexes. So where I start with y, I map y to the cone of F, and there is a map from the cone to the x. But if you look at the definition, this is only to the x shifted by 1. So the second part is actually immediately follows from the first part. You have a long exact sequence of homology. And the third part immediately follows from the second part. So F is a quasi-isomorphism. So for quasi-isomorphisms, I need a short notation. So let me call this just Q-ism for quasi-isomorphism. So what it means that F is a quasi-isomorphism, if you go back to the definition of the map between two complexes, you can clearly see that, so i.e., if you consider the map induced on cohomology, right? Because you have all these commutative squares, you have a map induced on the cohomology. So all these maps for any index supposed to be in isomorphism. So all these maps. So this map is an isomorphism, and this is for any I, which is integer. So this is the definition of quasi-isomorphism. So let me say this maybe in the parentheses. But the statement is the following, that the F is quasi-isomorphism if and only if cone of F is acyclic. So meaning that all the cohomology of the cone are 0. Or clearly this immediately follows from the long exact sequence for the cohomology. Okay, now I can define the triangulated structure on the H of A. So definition, a distinguished triangle in the homotopic category is a triangle isomorphic to the following triangle. So I have X, which is mapped to the Y by some map F. Then I have a map from the Y to the cone, and from the cone I have a map to the X shifted by 1. So all such triangles are distinguished, and all triangles isomorphic to such triangles are also distinguished. So with this definition of distinguished triangles, we have the following theorem, that the H of A is triangulated. So I don't want to prove this theorem, so the proof is exercise. So essentially you need to take the definition of the triangulated categories and check all the axioms using some explicit computations with the cones, and maybe you need cylinders to some of the statements. So the proof is, I would say, quite long. If I try to do the proof, I'll probably need today's lecture, next lecture, so I'd rather skip this and leave this as an exercise. Now I have also another exercise which is much easier, but I think this is still interesting exercise. If a triangulated category is abelian, say a triangulated category T is abelian, then T is semi-simple. So this is the reason why the homotopic category is rarely abelian, right? Because you know that the homotopic category is always triangulated. So if you additionally can prove that this is abelian, it means that this is a semi-simple category. So it's quite easy category. Okay. So do I need to define semi-simple categories? No, it means that, well, you have the abelian structure, right? So you have short exact sequences. And semi-simple means that any such short exact sequence splits. Right? So this is isomorphic as an exact sequence to the x prime. Here we have the sum, x prime and x double prime, x double prime. A typical example of a semi-simple category would be something like modulus over semi-simple ring or semi-simple algebra. So for example, modulus of the group ring, say with complex coefficients of a finite group. Okay. Now finally I can define the derived categories. To define derived category, I need to assume that A is abelian. Right? So notice that you can prove that the homotopic category is triangulated for any additive category. We haven't used that A is abelian, but to define derived categories, you need to assume that A is abelian, because you need to know what's a quasi-isomorphism is. You need to know the notion of the exactness and homology. So let A be an abelian category. So set AC of A to be the full triangulated subcategory of the homotopic category of all acyclic complexes. If you return to the definition of a triangulated subcategory, you can immediately check that all acyclic complexes form a triangulated subcategory. That's easy. And remember that when we discussed the localization of the triangulated categories, the so-called Verdier quotients, we also associated some the class of morphisms with the subcategory. So what are morphisms in this case? So morphisms of the subcategory AC of A. So can you tell me what's this class in this situation? Yeah. So these are exactly let me use maybe notation like this, U-ism. So all the quasi-isomorphisms, well, let's use A. Right? So by definition, the morphisms that they associate to a subcategory was all the morphisms such that when you take this morphism, complete this to a distinguished triangle, well, you get something in this category, right? So you need to take morphism such that the cone of this morphism is acyclic. Well, this we already know by that exercise. These are exactly quasi-isomorphisms. So this result follows from this. Okay. So definition. Derived category of A is defined as the Verdier localization or Verdier quotient of the homotopic category modulo subcategory of the acyclic objects. So later we're going to need several versions of the derived category. So maybe let's introduce this immediately. So some notation. So you can define the category of the complexes C+, the homotopic category H+, and the derived category D+. So the definitions are exactly the same as before, but you have some restrictions on the objects. So objects in this situation, so So objects being complexes with the property that the components of these complexes are all 0 for all sufficiently large negative indices. So essentially, this is something that sits in the positive part for the indices, maybe up to some finite shift. So this is the first, and of course you can define the C minus of A, H minus of A, and the D minus of A. So by saying the same words, except now the condition is that xi is 0 for all indices sufficiently large and positive. And finally, you can define Cb of A, Hb, B is for the bounded, and dB of A. So the same definition as before, but now condition that xi are all 0 for all sufficiently large indices in absolute value. So in this case, you have only kind of finitely many objects in the complex, and then you have zeros on the left and zeros on the right. So here you have zeros only on the left, and here you have zeros only on the right. Just some notation. So proposition, the embedding of the category D with a star to the category D of A. So where this star could be plus, minus, or B. So for all these versions, you have clearly have the embedding, right? So any such triangulated category sits inside the derived category. So this embedding gives an equivalence of the D star of A with the full subcategory of all complexes. Now the condition being not in terms of the complex but in terms of the cohomology. So with the condition that the cohomology hi of x is 0 for, and I have the same conditions. So for I sufficiently large and negative, this is the case, well, sufficiently large or positive, or something like this. And this, of course, for plus, minus, and B respectively. So, of course, in these three cases, the proofs are essentially the same, so it's enough to prove only one case. So, for example, let's consider the first case. Or maybe actually what I've prepared is the proof for the second case, I think. So you take a complex. Okay, so you take a complex and say this is -2, -2. So this thing is the complex, and I assume that for all sufficiently large positive indices, the cohomology are trivial. So let's say this is a proof for the case with the minus. So, and this P is the last position where I have some non-trivial cohomology. So I assume that cohomology of the HI of the X are all equal to 0 for I larger than P. But now I can take the truncation of this complex. So I take the same elements as before. So starting from the minus infinity up to the x p. Right. So well, I finish with this position, and instead of using, so this is 1, this is 1, and here I just take the kernel of the map, kernel of the differential, and have the embedding of the kernel of the differential here. And then I continue with the zeros. And I have 0 maps here everywhere. Now we can see that this is the complex with the trivial cohomology starting with some position p plus 1 and so on. And this is the complex that actually has a trivial component starting with the position p plus 1. And this map here is clearly as a quasi-isomorphism. So that's all we need to prove the statement. Exercise. So there is another version of this situation. So you can consider the embedding of the abelian category A into the derived category. Right? You can take any object. I consider this object as a complex that has only one non-trivial component in degree 0, which is given by the object. So this embedding gives an equivalence of the abelian category A with the full subcategory of all complexes X, with the condition that the cohomology of such complexes are trivial, so all are 0, for I not equal to 0. So you can identify such complexes where I have all cohomology trivial except one position. This position is being 0 with the abelian category A. Okay. So, and I want to finish this with another notation. So, this is not about subcategories, but it's just useful notations, for example, to formulate the next statement. So, I can consider complexes that live in degrees starting with A. So, these are complexes such that xi is equal to 0 for I smaller than A. So, and of course you can, well, for example, if you consider, say, C+, you know that there is such I. If you consider C+, you know that there is such A, right? So sometimes in the notation it's useful to know what's exactly the A, just to be precise about the situation. Okay. So now I want to start new section, the resolutions. So we have the following technical but important lemma. So let's see, be a full additive subcategory of an abelian category A. And let's take complex X in this C. Well, I'm using exactly the same notation as I just introduced, with this C that starts with some position A and continues to the right. So C larger or equal than A of this abelian category. So for some A being integer, if for any object T in the category A, there is a monomorphism of the given object T into the, say, object Y with Y being in the category C. So if you have this for objects, you can conclude that you have essentially the same property for complexes. So if there are monomorphisms like this, so then there is a complex sitting in the same degrees, so starting with some A and continue to the right, but now the components of this complex are objects in the C. So there is a complex Y and quasi-isomorphism X to the Y. Okay, so can you give me an example of an additive category A and additive subcategory C such that we have this property, that we can embed any object into some object in the C? Mm-hmm. Yeah, so for example, you can take A to be, say, all the modules over a ring, right? And you take C to be all the injective modules over this ring. And later, why this is important for us, we're going to take something like C to be, say, quasi-coherent shifts on some projective variety, and A to be injective shifts on this projective variety. So this is not just completely a kind of abstract statement. This I can in the statement I can use to begin with. I can use injective objects, but all I need in the proof is just this property. So I decided to formulate this as some abstract property with that this implies the existence of such quasi-isomorphisms. But of course, the main application is application to the injective objects, and this allows us to construct. You start with any complex, you can construct a complex of injectives which is quasi-isomorphic to the given complex. This is why I call this resolutions. So this lemma allows us to construct injective resolutions not for the objects in the abelian category, but for complexes. And of course, you can dualize everything, and instead of injectives, you can use projectives and prove the dual statement. Of course, the only technical requirement is that you have enough injectives in the category or you have enough projectives. Otherwise, it won't work. So proof. So the proof will be by the induction. So by induction. On P. So now I need to introduce this P. So we construct complexes y less or equal than P. So this is something like a partial solution to the problem. So such complexes and maps. So where I start with a given complex x. So this is P minus 1. This is mapped to the xp with the differential dp minus 1. Then the next differential is dp. xp plus 1, etc. And now from this complex I have a map to the complex y. So this is p minus 1 yp. This is fp minus 1 fp. So this is the solution of our problem only up to the pth partition. So in principle, if we need to show that we can start somewhere. We have the base of the induction. So we have this, and then we can construct the next step. So if we can do this, we have the proof. Okay, but actually we have the following. Well, have the following conditions for cohomology is enough. So if you consider the induced maps on cohomology, hk of the x is mapped to the hk of the y less or equal than p. So this is an isomorphism for k less than p, and monomorphism for k equal to p. Okay, first of all, what about the base of the induction? Well, if I have p which is less than a, well, this is very easy, right? So then in this case I can just take the 0 for y, right? So take y to be just a 0 complex. So now we need to do the step of the induction. So assume that we have y for the p for some p. So we construct y less or equal to the p plus 1. So we're going to do the next step in the induction. Okay, so maybe I start with the definitions. So I want to introduce some zp. So this is the fibered coproduct of the cokernel of the differential for the complex y with the index p minus 1 over the cokernel of the differential for the complex x with index p minus 1, and the second factor in this fibered coproduct, fibered product. So this is the kernel dp plus 1x. So this is for the CP, and for the WP, well, I have almost the same formula. Well, it's not supposed to be clear what I'm doing at the moment, so it will be easier to understand just a minute later. So let's start with these two definitions. Now, how we can understand these two objects. We can consider the following diagram. Well, the exactness of the first row that I'm going to write just follows from the definition of the cohomology. So HP of x, so the pth cohomology of the complex x, can be embedded into the cokernel of the differential with the index p minus 1. Then this is mapped to the kernel of the differential with the index p plus 1. And the cokernel of this map is the cohomology with the index p plus 1. Just use the definition of the cohomology and check this. This is an easy part of the diagram. Now here I have the identity map to the cohomology. So I'm going to now write the second row of the diagram. Now this cokernel of the D with the index p minus 1 for x is mapped to the cokernel for the second complex y, right? Because we have a map of complexes. And now you can see that that's exactly, so these three objects are exactly the objects that we have in the definition of the ZP. So ZP, we have this co-Cartesian square, and the ZP is living here. And using the universal property, I can get a map from the ZP to the H with the index p plus 1 of the x. And here I have the identity map again. Yeah, and of course, you can see immediately from these two definitions that WP can be embedded into the ZP. Because we have the embedding of these things. Okay, so exactness of this part is trivial. Now I have this co-Cartesian square, and I claim that the property this is co-Cartesian square can be used to show that the second row is also exact. So this is exact, and this is exercise. So maybe I will include this exercise in abstract form, not for this particular application, but in general in the second assignment. But that's an exercise in abelian categories, essentially, not in triangulated categories or derived categories. Yeah. So, and of course, we can also notice that this cokernel is exactly the cohomology of the complex y at the position p. Okay, now I can use this commutative diagram to construct. So on the next step, I need to find some object y with an index p plus 1. I need to construct a map fp plus 1. and I also need to find the differential. So this is dp. Now this is x, and this is y. So the goal is to find this part such that the square is commutative and we have all the right properties for the homology. Okay. So, well, but we have the property that we can take this object WP and we can embed this into some y p plus 1 such that this y with the index p plus 1 is in the subcategory C, right? What is the name for the subcategory? I think it was C. But in the statement we know that we can take any object and can embed into, well, we have the monomorphism to the object in the C. So we have this map. Now I want to define f with the index p plus 1 as the following composition. I have a map from the x p plus 1 to the wp, and then I have combine this with the map to the y p plus 1. Right, so the existence of the first map just immediately follows from the definition of the WP. So that's the map of the complexes, and now I want to define the differential dp. It's, well, I think this is a composition of the three maps. So yp is mapped to the, of course by the definition, to the co-kernel of the dp minus 1, right? Now this is mapped again by the definition of the WP to the WP, and finally I can embed this into the yp plus 1. So I claim if I take these maps as these compositions that everything works. Probably this is not clear why this works. So I try to justify with the following commutative diagram. So first of all, I start with the definition of the WP. So I have somewhere here co-kernel for the differential on the complex x with the index p minus 1. So this is mapped to the co-kernel of the differential on the y, and this is mapped to the x with the index p plus 1. Now the co-Cartesian square give me maps to the WP. Right? So this is still the definition of the WP. There is nothing new here, right? Yeah. Okay. Now from the WP I have this map to the y p plus 1. So I want to put everything on one commutative diagram. Then I have a map from the xp to the co-kernel of the differential on x. And I have also yp. So here the map is fp. And I have canonical map to the co-kernel. Clearly this square is commutative, right? Because this map on the co-kernels is just the map induced by the map fp. Okay. Now this map here is the differential. By the definition, if you take this whole composition, right? So if you take this, maybe I need to, I don't know what would be the best way to do this. So if you just look at this composition, then you'll get the new differential, right? And if you look at this composition, then you'll get what I called fp plus 1. But now if you just look at this diagram and look at the definitions of the dp and fp plus 1, you can immediately see that commutativity of this square follows from the commutativity of the diagram. Okay, so I need to erase something, or maybe I can continue on that last piece of the blackboard. So the last thing that I need to check is that I have isomorphism and cohomology. So let's do the computation. So if I want to compute this cohomology, well, I can think about this cohomology as the kernel of the map of the co-kernel of the D differential on the y with the index p minus 1, which is mapped to the y with the index p plus 1. So I hope you can check that my computation syntheses are correct. So this just follows from the definition of the cohomology. There is nothing here but the definition. Now, from the commutativity of the diagram, I can replace this kernel with the kernel of the map from the co-kernel of the D1y, which is mapped to the ZP. So this first part is essentially equivalent to the definition of the cohomology. Now the second isomorphism follows from the commutativity of the diagram. But if you look at this, again, this is using the definition of the cohomology, we can conclude that this is HP of the X. Well, that is for say this is for index P, and of course this is true for any indices which is less or equal than P by induction. Now the only step that we need to check is that if I take HP plus 1, so the cohomology at the position P plus 1 of the complex X, again, definition of the cohomology tells us that this is the co-kernel of the differential, which is mapped to the ZP. This part again follows from the commutativity of the diagram. I just look at the second line of the diagram. So we have this isomorphism. Now we can clearly embed this co-kernel into a larger co-kernel, where we have co-kernel of the D P minus 1y. Now I embed this not in the ZP, I embed this in just YP. And the last thing again, essentially this is definition of the cohomology. This is HP plus 1 of the y less or equal P plus 1. And so we finish the proof. It was a little bit technical, so maybe you want to think about this. So you want to maybe think why this second line that the commute in this diagram is exact. Maybe you want to analyze this commutative diagram and see that this commutative diagram implies the commutativity of the square. And well, I don't know, maybe think about these computations also. Okay. Now we can combine this technical lemma with another exercise on triangulated categories and get an interesting result. So, exercise on triangulated categories. So let C and D be triangulated subcategories of T. So of course T is triangulated. Now I have the following assumption. If for any object X in the category D there is a map x to the y with y in the second category, so y is in C, and if you take this map and complete this map to a distinguished triangle, then the Z in this distinguished triangle is again in C. So if you have this, then the conclusion is that you have the following equivalence of triangulated categories. You can take a quotient of the C by the intersection of two triangulated subcategories, C and D, have a canonical functor to the quotient of the D of the T by the D, and this gives you an equivalence of triangulated categories. So then there is an equivalence of triangulated categories like this. Example. So where this is useful, now I take triangulated category T to be the H plus of some abelian category A. So where A is abelian category, with enough injectives, so let's also fix some notation. So let I of A in A be injectives. So be full subcategory of injective objects. Okay, so I have category T. Now I want to define D and C. So D in this example will be all acyclic complexes, so acyclic plus of A, and C, this is the homotopic category, H plus, of the injective objects. So this is the place where it's important to know that homotopic category can be defined for any additive category. So there is no reason to expect this is abelian again. But at least this is additive. So this makes sense. We have some triangulated subcategory C. So now I claim two things. Well, actually, so in this case, intersection of the C and D is trivial. And do you know that this is trivial? Again, I claim this is something that you probably have seen in the basic homological algebra. For example, when you discussed injective resolutions of objects. Right, so here, Well, you say the thing you can do, you can, for example, take this injective complex, right? So you want to take, you have, what do you have in the intersection? You have injective complex of injective objects without cohomology. So acyclic complex of injectives. So then you can take, for example, the identity map, and using that all the objects are injective, you can find the corresponding lifts, and then you can show that the identity map is homotopic to 0. And for this reason, C intersect with D is just 0 because any object will be isomorphic to 0. Okay?
So I have a question about the exercise.
Mm-hmm.
Because it doesn't say anything how C and D relate to the
Oh, we definitely need to exclude this case that C is E and D is 0, so maybe non-trivial triangulated subcategories. Oh. This can be fixed. But do you have any other problems? I don't think so. Okay. So we have this intersection 0. Now let's apply the exercise. So in this case, we see that the C, which is the homotopic category, H plus of the injectives of the abelian category A, and this is supposed to be equivalent as triangulated category. Now we need to take the quotient of the H plus by the D, so by the AC plus. But that's by definition D plus of A. Oh, I'm not sure this is a problem. Why would this be a problem? Well, if you try to change the category T, you can change all the. Well, you can change how you can complete from the map to the distinguished triangle. Okay, so I still believe that the statement in the exercise is correct. Okay, anyway, so the main result that we need this exercise, well, why we need this exercise is this. And why this is useful, well, remember when we discussed the derived categories, the Hom set was just the set of all the roofs with some equivalence relations, so there was a problem why this is even a set, right? It's not clear that all the roofs form a set. So if you have this situation in abelian category with enough injectives, you have this equivalence, and you automatically solve the problem. So this is one of the philosophical remarks why this is important. And another reason why this is important, this allows us immediately define derived functors. So there are two approaches to derived functors. You can define them using some universal properties, or you can kind of explicitly define them using this equivalence of triangulated categories. Derived functors. Well, if you have two abelian categories, so let A and B be abelian categories. So any functor between abelian categories can be extended to homotopic categories. So H of F this is a functor between homotopic categories. So this is always possible. Now, of course, what we want to do is the following. We have homotopic category. There is a localization functor to the derived category. There is a functor between homotopic categories. So another localization functor. So can we find a functor between the derived categories and so on? And can we call this derived functor of f? So unfortunately, this doesn't work in general. So when this works, well, to define a functor like this on the quotient categories, you need the property that this h of f maps a cyclic complex to a cyclic complex. So this thing has to be exact. So this works only if h of f applied to a cyclic complex sits again inside the acyclic complexes OP. So it maps a cyclic complex to an acyclic complex, and that's one of the definitions of an exact functor. F is exact functor. But in general, this of course doesn't work. So what we can do is the following. So let's take this homotopic category of A, map to the homotopic category of B. So here we have the localization. Well, now let's restrict everything to the plus situation. So this is H plus of A, H plus of B, and D plus of B. So there is a localization QA to the D plus of A. Now inside H plus of A, we have H plus of the IA of injectives. And this embedding, we know that this gives an equivalence of the H plus of the IA with the derived category. So it means that there is a functor going in the other direction. So maybe let's call this functor phi. So now we can use the following definition. So let's define the right derived functor of a left exact functor f. So now I assume that functor that I start with f is left exact. And I define the right derived functor. Now sometimes this is also called the right total derived functor, acting on triangulated categories, as the following composition. So the notation for this is RF, and the definition is the following. You just take the composition. So you start, you have some object in the derived category of A, you apply functor phi first, right? Then using this embedding, you'll get something in the homotopic category H plus of A. So you can compose this with the homotopic functor H of f. And then finally, you can look at this answer and apply to this answer the localization QB. So essentially, you can read the definition as follows. You take an object here, you replace this object with an injective resolution, and we know that we can do this by the lemma. Then apply to this injective resolution functor f kind of component-wise. This is what we do when we extend this to the homotopic category. And then just look at the complex that we obtained and consider this complex up to quasi-isomorphism to get an object in the derived category. So quite straightforward definition. And this will be our definition of the total right derived functor. Now, This is the total right derived functor. Well, sometimes people also introduce the following notation for the cohomology. So Ri of f, this is by definition, if I want to compute this on the complex x, well, I need to apply the total derived functor and then take the cohomology, hi. So in particular, we can see that we get some functors. Well, we can, in this complex, instead of the complex x, we can take just an object in abelian category. Right, so then we'll get some functors Rif from A to B. So these are additive functors. So there's a total derived functor, and there are this kind of components of the derived functor on the abelian categories. Now, why I want to assume that my functor is left exact? Well, that is because, for example, if I take x without a bullet, so I assume that x is just an object in A, so how am I supposed to compute the derived functors? I need to take this x and replace this with the injective resolution. Right? So then I take this injective resolution and apply f to this injective resolution. And then take the cohomology. Yeah, so the cohomology, maybe I write something like this. Hi of this thing is Ri f of x. But left exactness give me the following, that the R0 of f of x, this is just the f of x. This is why I need the left exactness. So the zeroth component of the derived functor is the original functor, and I have some higher derived functors, Ri of f. And together, we can think about this object as a functor between triangulated categories, and this is just cohomology of the result when you apply the total right derived functor. Okay, so I think I'm out of time, and we continue this next time.